Lab number 9. All right, for this presentation, we are going to be covering lab number 9. This lab was completed by the Borcel Group. In this experiment, we are focusing on concepts related to physics, specifically forces, motion, and magnetic fields. You can also see some of the key equations and visuals around the slide, like Newton's second law, which is written as F equals m times a, meaning force equals mass times acceleration. These ideas will help us understand how objects move and interact when forces are applied. Slide 2, materials. Now let's go over the materials that were used in this lab. First, we used coils with different numbers of turns. These are important because the number of loops in a coil can affect the strength of the magnetic field it produces. Next, we used a magnetic field sensor. This tool allows us to measure the strength and direction of the magnetic field generated during the experiment. We also used a power supply, which provides the electrical energy needed for the system to function. Finally, we had a voltage and current sensor, which helps us measure how much voltage and current are flowing through the circuit. All of these materials work together to help us collect accurate data and better understand how electricity and magnetism are related. Now let's go over the introduction for this lab. Magnetic fields are created by moving electric charges. In simple terms, whenever electricity flows through something like a wire, it produces a magnetic field around it. The behavior of these magnetic fields can be explained using something called Ampere's law. This law tells us that the strength of the magnetic field around a wire depends on how much electric current is flowing through it. So, the more current there is, the stronger the magnetic field will be. For a long, straight wire, the magnetic field gets weaker as you move farther away from the wire. However, when the wire is shaped into a coil, things change a bit. The magnetic fields from each loop of the wire combine together. This creates a stronger and more uniform magnetic field, especially inside the coil. So overall, this lab helps us understand how electric current and wire shape affect the strength and behavior of magnetic fields. Now, let's walk through the process step by step. First, we turned on the computer, opened the Capstone program, and connected both the voltage current sensor and the magnetic field sensor to the Pasco interface. Next, we set up a 200-turn coil and secured it in place using a clamp. Then, we connected it to the power supply and the voltage current sensor using wires. After that, we created a graph of current versus time, where current is on the y-axis and time the x-axis. We also set the capture rate to 100 Hz and the maximum current to 10 amps. Then we tested the setup to make sure everything was working properly, including checking that the power supply was delivering the correct current. Once everything was verified, we ran the experiment using the 200-turn coil and recorded the magnetic field data in a table. After that, we repeated the experiment using a 400-turn coil, then an 800-turn coil, and finally a 1600-turn coil, recording the results each time. This allowed us to compare how the number of turns in the coil affects the magnetic field. Now let's go over the data analysis. From our results, we measured the magnetic field strength for coils with different numbers of turns. For the 200-turn coil, the magnetic field was 5.7 times 10 to the negative 5 Tesla. When we increased to 400 turns, the magnetic field increased to 1.13 times 10 to the negative 4 Tesla. Doubling the number of turns from 200 to 400 resulted in about twice the magnetic field, with a ratio of about 2.00. This same pattern continued as we increased the number of turns. At 800 turns, the magnetic field was 2.30 times 10 to the negative 4 Tesla. And at 1600 turns, it reached 4.57 times 10 to the negative 4 Tesla. Each time we doubled the number of turns, the magnetic field also approximately doubled, with ratios close to 2. This shows a direct proportional relationship between the number of turns in the coil and the magnetic field strength. Overall, our data closely matches the expected physics principle that increasing the number of turns in a coil increases the magnetic field strength proportionally. To conclude, our experiment confirms that the magnetic field inside a coil is directly proportional to the number of turns. As we increase the number of turns in the coil, we observed a consistent increase in the magnetic field strength. When the number of turns was doubled, the magnetic field also approximately doubled. This matches the expected physics principle and supports what we learned from Ampere's law. Overall, our results were consistent and showed a clear pattern, confirming the relationship between coil turns and magnetic field strength.